The overall goal of this procedure is to demonstrate a highly efficient method for generating terahertz radiation. This is accomplished by incorporating plasmonic contact electrodes in photoconductive terahertz emitters to enable high quantum efficiency and ultra-fast device operation simultaneously. The first step is to fabricate plasmonic photoconductive emitter prototypes using electron beam lithography. Next, the radiation power of the implemented emitter prototypes is measured and compared with identical conventional photoconductive terahertz emitters without plasmonic electrodes. The final step is to characterize the spectral properties of the radiation from plasmonic photoconductive terahertz emitter prototypes. Ultimately, results are obtained which show that incorporating plasmonic electrodes in a photoconductive emitter could enhance the radiation power and efficiency by 2 orders of magnitude.
This method can help address the main limitation of conventional photoconductive terahertz emitters, which is the trade-off between high quantum efficiency and ultra-fast operation of conventional photoconductors.
Conventional photoconductive terahertz emitters consist of a terahertz antenna integrated with an ultra-fast photoconductor. Terahertz electrical currents are produced for this antenna when an optical pump beam with terahertz frequency components is focused on the ultra-fast photoconductor. This beam generates photocarriers at a rate proportional to the envelope of the optical pump. With the application of a bias electric field, the photocarriers drift towards the contact electrodes